Okay, let's start. So I don't know what time is it at your place, but good morning, good afternoon, or good evening. Welcome to this workshop, dive into the Copernicus Marine Service. This is session 2 of this event dedicated for America, Marine Data for America. I'm F.Messal. I'm training and education manager at Mercator Ocean International in France. And I will be your host. Let me introduce you Paola Agostini. She's a science manager at CMCC, the Centro Euro-Mediterraneo for the climate change, and she will be your moderator. Hi, Paola.
Hello, everybody.
Paola, the stage is yours.
Yes. So welcome back. I hope you enjoyed the sessions of yesterday. Today, we are going to reply the same format with much more information about the Copernicus Marine Service. So next slide. As you may recall, this is, and as Fabrice said as well, this is the last day of 3 days event. Last week was the webinar, the introduction to the Copernicus Marine Service, the website, and some experiences of users already of data from Copernicus. And yesterday and today, we are instead going into much more details about the products that are available for your interest in the area of interest in the Copernicus Marine Service catalog. And yesterday we saw some of them, and today we are going to see others, as well as some practical sessions. In particular, you will see other products derived by either in situ observations or other data products, and also the modeling products. And then you will have the demonstration of the Jupyter notebooks that are all the exercises that have been prepared for for you to exercise with this data, and also the RStudio demonstration. Next slide. So for the first part, for the general introduction to other groups of Copernicus Marine Service global data, we have today other 4 excellent speakers and experts. So the first is P.Rotllan Garcia from the SOCIB Spanish institution, and she will introduce you to the in situ products. Then Vinca Rosmorduc from the French CLS will introduce you to the sea-level products. And for the modeling products, we will have first A.Dalphinet from Météo France about the wave products, and Masina from CMCC giving you details about the global ensemble products. Next slide. For all of them, or the 4 of them, will be available at the end of the 4 presentations of the products for your question and answers. So I remind you to use the chat in your training environment. And then after the demonstration, the 2 demonstrations, each demonstration, we will have as well the possibility to pose questions to the 2 trainers who are Francesco Palermo from CMCC for the Jupyter notebooks, and D.March Morlà for the RStudio demonstration. Next slide. So you will listen to the experts, and during the presentation, just after, you can put any question in the chat, and the questions will be then posed to the speakers. They will reply as many as possible to the questions. Otherwise, they will be replied after the workshop anyway. Okay. So you as participants are very encouraged to pose any questions to the experts that are here for you today. And I pass the floor again to Fabrice.
Yes, just a few words about all the training material prepared for you. So the experts and developers spent a long time to prepare all the Jupyter notebooks available on the Jupyter Hub platform. Each notebooks have its own tutorial video recorded by the experts, and you will find on the Copernicus Marine Service e-learning material webpage a lot of material videos on GIS, on how to download the data, etc., etc. So don't hesitate to have a look to this website and webpage. You will receive also the user manual with all the links to access to this material. So the Jupyter Hub is available and you can access directly if you are registered to the Copernicus Marine Service. As a reminder, the registration is free. So you can go on the Jupyter Hub directly and you have access to the different Jupyter notebooks. Don't hesitate to practice and to play with all this material. And we try to collect all the material available, videos, documentation, product presentation, I don't know what else, but a lot of material is available on our Padlet. You have the address here. And so don't hesitate to have a look to this Padlet and try to find the relevant material you need to continue your use of or your discovering of the Copernicus Marine Service data. So now I think we can start with the first panelist.
Yes, so as we said, we start now with an introduction to 4 groups of products available at the Copernicus Marine Service. And the first is about the observation products related to the in situ data. And the presenter is P.Rotllan Garcia from SOCIB. So Pat, the floor is yours.
Okay, thank you. Are you seeing the presentation? Yes? Thank you.
Yes. Yes.
Thank you very much for joining this 10-minute talk about the in situ observations. I'm P.Rotllan Garcia, and I'm here on behalf of Sylvie Poliquet, who is the actual manager of the group in charge of procuring this data in the Copernicus Marine Service. The in situ thematic assembly center, or the in situ TAC, is also called like that. I hope I will do it properly. Just so we are all on the same page when talking about in situ observations, I just wanted to let you know that this data is the kind of data procured by a wide range of platforms, like the one you can see here: vessels, gliders, moorings, HF radars, drifters, and so on, which are deployed in the ocean with the only objective of measuring certain variables like temperature, salinity, currents, and waves, and so on. So this kind of data is completely different to the other kind of observation that you are going to find in the Copernicus Marine Service, which are the satellite observation. This approach, the multi-platform approach, sets some particular features to the resulting products that I wanted to share with you, so that it's not a surprise. The in situ products usually have gaps, because obviously we only have data where there is a platform reporting data. If there is no platform in a given area, we don't have information in such area. This happens. Another thing is that you will find many different shapes of data because it depends on the kind of platform reporting the data. For example, you will find time series, but also profile data, and also trajectory-like data. So there is no only one geometrical shape for the data in the in situ products, but several ones. Another typical thing is that there is no homogeneous resolution, because in the end, the sampling interval is set by the operator of the platform. And as there are many operators, there are many sampling resolutions. So this can vary in a given product. These are the top key 3 features that I wanted to share. The purpose of having this kind of data in the Copernicus Marine Service catalog is for it basically to be used in the assimilation and validation task to improve other products in the catalog, like the satellite products and the model products. And if your institution is involved in similar tasks, I can invite you to use this data for the same purpose. This is a list of achievements accomplished so far regarding the in situ observations available in the Copernicus Marine Service, and I just wanted to highlight 2 of them. The first one is the heavy standardization of the in situ data regarding format, but also procedures. And the second one is the collaboration, the strong collaboration with other initiatives like Eurobus, CDataNet, and Monet, in order to procure the most complete data products as possible. This is the scheme of the work carried out by the Situ TAC, the group that I told you is in charge of procuring this data within the Copernicus Marine Service. As you can see, it's focusing mainly in maintaining 2 streams of data: the near real-time data, which is intended for assimilation tasks, as I told you before, and the delay mode data, which is served as a reprocessed product and is intended for it to be used in the validation task I mentioned before. Then this other group is investing some time also in other activities, some obvious ones relative to the management and documentation, but some others are also worth mentioning to say, like the scientific exploitation of the data through the Ocean State Report, which is a journal, a supplement of the Journal of Oceanography that maybe it was presented to you on day 1. And also this group is maintaining a website that I will mention later, where you will find a lot useful resources to understand better the products and the whole workflow of the data. In this slide, I try to summarize the 2 family of products that you will find containing in situ observation in the Copernicus Marine Service catalog. The first one is the reprocessed product, and the second one is the near real-time product. And they basically differ in 4 key features. The first one is the update rate. For the reprocessed product, this is 6 months, and for the near real-time product, this is every hour. The second one is the scope. The reprocessed products is only produced for the global scale. Nevertheless, you will find for the near real-time products the global scale, but also regional ones. Then regarding quality mode, the reprocessed products are all the result of a delay mode quality control over the data, whereas the near real-time product is a mix of automatic quality controls and also delay mode quality controls. And the last difference is the topic or the parameter family they focus on. The reprocessed products is typically focusing on one single parameter family, such as currents, carbon, waves, BGC, and temperature and salinity. Whereas for the near real-time product, although you can find also dedicated products to certain parameters, the typical situation is the multi-parameter product. Okay, so this is just the summary. I hope this is useful for you. In this slide, I basically wanted to showcase the evolution of the different products per topic. I'm not going to talk about all of this because it started in 2015. I just wanted to mention the one that occurred in 2021, which was the inclusion of in the current reprocessed product of the current derived from Argo floats. Okay, and the second one is the inclusion in the near real-time products of the Monet chemistry data. These are the available access for accessing the in situ observational products. The main one is the FTP access, but also you have other access like the AirDAP services and F.Messal service. I just highlighted the AirDAP services because it was recently released. And with this one, you will have access solely to the last 60 days of data for the near real-time products. Also, regarding the F.Messal service, is only enabled for the interpolated products. two interpolated products that we are producing in the Copernicus Marine Service catalog containing in situ observations. So for all, at least for all the products, at least you have the FTP protocol for accessing it. Then I wanted to share with you some useful links, which are rooted in the marineinstitute.eu, which is the website I told you about that the group procuring this data is maintaining. So if you go there and check the documentation, you will find all a lot of material regarding the NFPA format manual, the parameter list, the quality control procures, and everything. So I kindly invite you to have a look to all this documentation because in this 10-minute talk, I don't have much time for this. Then you have also another section, which is the monitoring section. In here, you will find some metrics, which are basically computed over all the products, highlighting the delay of arrival of the data, the number of platforms, the data quality, the data providers, and so on. It's also useful for getting to know better about the content of the products. And then also you will have the dashboard in the marineinstitute.eu dashboard. This is just a friendly viewer for you to access interactively all the data, all the in situ observational data available in the Copernicus Marine Service. The last slide is just to highlight that this is not a straightforward line. As you can see, there have been very challenging peaks so far for the group, and we are mostly now focusing on providing feedback to the provider. It's a long technical depth to provide metrics of usage over the data that is showcased also in the Copernicus Marine Service. And the good news is that we are now with a pilot already working, and maybe for the next year we are able to provide an interface for the different providers to check the usage metrics of their data. The last slide is to show you what I have prepared for you to introduce you to the in situ observations. We will start with some by defining an area of interest and a time range of interest to analyze what kind of data is in there, so that you can evaluate if the product we are going to use is suitable for your need or not. Then we are going to perform some subsetting and download of the data files in there, and we are going to make plots like the one I'm sharing. I have tried to illustrate the different data geometries that you will find, like the profiles, the time series, and the trajectory like data, so that you are able to work on your own later. And that's all. Thank you very much. And if you have any question, I think you have a chat platform, and I'm ready to answer.
Thank you, Pat. Yes, as you just said, please post any questions you may have in the chat, and after the first presentation, we will address them together. Thank you, Pat, again. And we pass now to another category of observational products related to sea level. And the presenter is Vinca Rosmorduc from CLS. And Vinca, the floor is yours.
Thank you, Paola. Good evening or good morning, I don't know, to everybody. So I will show you what we are talking about when we say sea level. So the sea level product is about the fact that the ocean is not flat. No, the Earth is perfectly round. The ocean is bumpy. So I'll speak a little bit about what are sea level and satellite altimetry, which parameters are in the products available through CMAMS, and which satellite sea level products are in the catalog, and then some application outlines. So the satellite sea level is measured by a sensor we call altimeter on board of several satellites. Currently, we've got 9 satellites with 2 being calibrated. So you have 7 satellites within the data sets. The altimeter is measuring the sea surface height as a surface of the ocean with respect to a reference level. So the satellite here is measuring its distance from the surface of the ocean, and then onboard precise orbit determination helps to make the difference. And so we have a sea level absolute or sea level anomalies. So we are measuring the sea surface height by subtracting the altitude and the range, and then we've got a sea surface height with respect to an abstract surface called the ellipsoid, and we have various corrections involved from the environment, what is happening through the atmosphere when the radar beam is going back and forth, geophysical correction like the tides, and a number of corrections implied to have the most precise possible sea surface height and sea level anomalies. What you have to understand is that altimetry is not imagery for now. Basically, altimetry data are measured just beneath the satellites along a narrow thread. So what you can have is something like the figure here, which is made from several satellites. So each of the inclination is coming from a different satellite. So here you have 4 different satellites involved in this map, and each are producing its own mesh of lines along the Earth. So within the products, you will find the sea surface height anomaly, also called sea surface height with respect to a several-year mean. They are showing the variability of the ocean surface topography. And from these sea surface height anomalies, sea level anomalies, we derive geostrophic current velocities, which are computed from the surface slopes. Those include only the current's variability. We also have within the product the sea surface absolute height, called the absolute dynamic topography, which is the sea surface height with respect to the geoid. Oceanographers often call it sea surface height, but you should always have a reference because sea surface height for altimetrists are not this. So sea surface height with respect to something. And you have derived geostrophic current velocities, which are also computed from the surface slope. This time it includes also the mean currents flow and the variability. So the 4 parameters are available within the gridded products. So you have gridded products, which are fully filled maps with the sea surface heights and the derived variables I've just talked about. We recommend their use for mesoscale activity monitoring, geostrophic currents derived application, for example. But we also have the along track sea level sea surface height with only the real measurement made from each of the satellites. And then this is typically used for assimilation in numerical model, but you can use also them because you need to remove some of the correction like the tides, because you're in a very local area with bathymetry, which is producing particular tides. So you may need to remove the tides, and to remove them, you need to remove them at this stage. So those are the 2 main kind of data you will find. Both are available in real time and delayed time reprocessed. Those are of higher accuracy because we need time to compute the best possible orbit. So it depends what you need. If you need really recent data, you'll have to use the near real-time data. But if you want long series of data, or if you need quite old data, go to the reprocessed data. To find those products in the Marine Copernicus Service catalog, you can, if you click on Ocean Product, you can use the box to search for sea level without space, and then you'll have only the remote sensing measurement from the satellites. And you also have the ocean monitoring indicator in Copernicus catalog. So this is the full list of products available through the Sea Level Thematic Assembly Center. You've got the reprocessed and the near real time, the level 3, so the along track data, and the level 4, the gridded data. You see, you've got different areas. For the reprocessed data, you've got a Mediterranean area, while for the near real time, you've got only a European area where you have also European seas. You also have the ocean monitoring indicator, like the anomalies and the sea level variability. For global, Mediterranean, Black Sea in reprocessed, Europe in near real time, and there's a test data set with the Atlantic. A few examples of applications. You've got this figure which was made by our American colleagues from our data, showing in black the deep water horizon oil spill, and in color it's ocean color, it's sea surface temperature, and the arrows are the ocean currents computed from altimetry. So you see all are comparing very well, and you can use those surface current, geostrophic currents to have a better idea of dispersal or drift in the ocean. We can also see extreme event studies like storm surge, sometimes not considering the tides, removing the tides. So you've got an example on an Aqua Alta in Venice 2 years ago, where you see here on this map that the Sentinel-3A satellite is showing very high sea surface height, or sea level anomalies. The tides have not been corrected for once. The typical use of the level 3, as I said, is assimilation. So you can assimilate a long track altimetry product, a long track sea level product, to fit the model with what is really happening in the ocean. So you are gaining some accuracy in doing so. And I stole this example for D.March. You will see later on with our computing programming. This is a turtle tracked by Argos in the Mediterranean Sea 2 years ago. And you can see it's going around the sea surface height topography. This is not the temperature, even if it's blue and red, it's the height. So you see, yopla, so the turtle is going round and going faster around the edges than outside. So those are the kind of things that you can see with altimetry, and you can also study only the current from it, of course, but the turtle help explaining and showing the reality of those currents around eddies. So thank you for your attention, and if you have any question, I'll be available to answer them later on. Thank you.
Thank you, Vinca. Yes, there are some questions that we will see later, and the participants can still post them in the chat. We go now to the next presentation, and we start now with seeing other products derived by modeling. In particular, Alice A.Dalphinet from Météo France will introduce you to the products derived from modeling of waves. And Alice.
Hello, everybody. I'm Alice A.Dalphinet from Météo France. And I'm going to present you the web model products of Copernicus Marine Service. In the web team, there is also Lotfi Aouf and Stéphane Lochun. So our main product is a near real-time web model. You may recognize this table, which is taken from the Copernicus website. We are using the web model called MF1. We are running it every day, and there is an analysis and also 10 days forecast that are available. We are providing a very classical integrated parameters of the sea state. There is, for instance, the wave height, mean period, and direction for the total sea, but also for the wind sea part and for the first and second swell. We are forcing the wave model by ECMWF winds and also by the global physics surface currents. We in the Copernicus website, you have 2 years that are available, and it is a 3 hours time step on 1/12 degree grid. So we are assimilating altimeters data for the hindcast. Today there is 6 altimeters in near real time. They are all available in the wave thematic assembly center of Copernicus Marine Service. And you have here the spatial coverage for 1 day. You see there is a very good spatial coverage thanks to this network of 6 altimeters. For instance, also in Gulf of Mexico or in Caribbean Sea. And we are also using the wave spectra to correct the model. The wave spectra from Sentinel-1 A and B and CFOSAT. So this is a very variable information with the energy depending on direction and frequencies. And it permits us also to correct the direction and the period in the wave model. So it's very interesting data. The last satellite that we are using is CFOSAT. We have evaluated its impact in the web model. So you have here an example of the impact of its assimilation in the web model for the Austral Ocean. It is very interesting to see it in this part of the world because CFOSAT is very well adapted to long wind sea. And in the ocean, in Austral Ocean, there is very long wind sea, and thanks to these satellites, we can correct the bias. At the right, it is the bias without the assimilation of CFOSAT, and thanks to CFOSAT, we have reduced this bias. I insist now on another characteristic of the wave model. It is the forcing by the daily currents of the global physics ocean model. So it is important in area where there is a strong regional current. For instance, you have here an example of the currents at the right. It is a North Brazil current, and at the same date, you have the significant wave height of the global model at left, and you recognize the pattern of the surface currents in the wave height. And in area where there is a current of more than 0.5 meter per second, it impacts significantly the wave height and the wave period. So it can be an enhancement or the opposite. It depends on the direction of both fields. And we can also have an important impact in near Brazil coast. We have done a validation of the wave model thanks to independent data. We have used, for instance, the altimeters HY2A and B, and it has permitted us to see that the bias is around minus 20 centimeters and plus 20 centimeters. The normalized error is very good in deep ocean in tropics, around 5%, and we go up to 15% in nearshore area or in specific place like Gulf of Mexico. We have also used the buoy data to validate the model, and for that we use the database of the in situ team, which is very valuable for a modelizer. And we have almost no bias, and the relative error is around 14% for the wave height and 10% for the peak period. I come now to the second main product about wave model. That is the wave reanalysis, which is called Waveries. It consists in 27 years of a wave field at 0.2 degrees. This is always a MF1 model, but it is forced now by Era 5 winds and by Growis surface currents. We are simulating the wave heights of the altimeters. We have chosen this period because it is the beginning of the altimeters period. So since 27 years, we have altimeters data that are available. And we are also assimilating the spectra of Sentinel-1. So you have the same integrated parameters that are provided every 3 hours at 0.2 degrees. It is these data are very interesting to compute climatology, wave climatology. I give you here some example of very classical statistics. For instance, 19th percentile of significant wave height, and it is also possible to compute wave rows thanks to this 27 years, and it is long enough to contain a lot of extreme events, and it permits to have a quite precise wave rows, even quite near the coast, because the resolution is 0.2 degrees. Regarding the extreme, we have a look at them. For instance, during the comparison against HY2A, you have here the result of this comparison, and we have the chance to the opportunity to have observation of HY2A more than 8 meters, and you see that the simulation of Waveries is quite good at for this very strong wave height with no bias. And we have also compared with buoys data. This is an example here in Austral Ocean. During the maximum record of the buoy, we have seen that there is an underestimation of the period on significant wave height, but the waveries remain quite well correlated with the observation. So recently we have added the satellite CFOSat in the assimilation for the nadir wave height and also for the spectra. We have just added it in February 2021. We produced since last year a 10 days forecast, and in the next future we want to refresh the forecast twice a day, or not only once. And we are also planning to produce regular scores against observations. And regarding the reanalysis, we recommend we have published a paper. You can see more details about our results in this paper. I give here the references. And for this year, we are planning we have just compute the last year, 2020. We are very soon, we are delivering it very soon. And we want also to implement an automatic update of the reanalysis product. So I thank you for your attention, and I will be glad to answer your questions.
Thank you, Elise. Yes, questions are coming, so we will have time to look at them. But first, the last presentation, the last group of modeling products, a special group of products about reanalysis, the multimodal ensemble products. And the presenter is Simona Masina from CMCC. So Simona, the floor is yours.
Yes, thank you, Paola. Let's see if it's working. Do you see?
Yes, just the presentation mode, probably.
Yes. Okay, I guess you now see my screen.
It's coming.
It's coming.
Yes, it stopped now. I don't know if it's only for me or if it's.
It appeared on my screen in full mode.
Okay. Try again. Maybe just we go back and try again. Unless you want me to do it. I have it. I have your presentation. Maybe we can try it. Let's see.
If you prefer,
let's see if it works, and then.
Yeah. That. Okay. Okay.
And you tell me when to go on.
Okay, thank you. Sorry for the inconvenience. Okay, so I will continue this overview of the Marine Copernicus products with a special product that is an ensemble, a multimodal ensemble of global reanalysis. I'm Simona Masina, and with my colleague Andrea Cipollone at CMCC, we did this presentation. We are at CMCC one of the 4 producers of this multimodal ensemble. Okay, Paola, you can continue. Also, the previous speaker mentioned reanalysis, weight in reanalysis in her particular case, but what is exactly a reanalysis? Just to make clear what this term means. A reanalysis in our community, well, also in the atmospheric community, let's say, is a retrospective estimate of the ocean state that uses the same ocean general circulation model, the same data simulation scheme, and the same atmospheric forcing through a long period. So usually reanalyses are designed for climate applications, and they differ from what we usually need as the best estimate of the day, as the best estimate to initialize forecasting. They differ because their aim is not to produce the best estimate of the day, but the most coherent and consistent state of the ocean, in our case, throughout a long reanalysis period. Please, the next slide. So the main components of an ocean reanalysis are shown in this slide. First of all, you use an ocean model, in our case, a global ocean model, because we are talking about global reanalysis. You need an assimilation scheme that can go from very simple optimal interpolation scheme to very sophisticated 4D VAR or ensemble Kalman filter. You use a forcing, an atmospheric forcing, and you use and you need, all these data that have been mentioned and presented during the first two talks. So all the in situ data, temperature and salinity coming from different observational network, the altimeter data, and in the case of the global ocean, also the sea ice concentration data. Next slide. So the Copernicus, the Marine Copernicus service, maybe it has been presented already to you, covers the several regional seas and the global ocean. Please go on. Yeah, okay. And for each of the regional seas, so for example, the Arctic, the Baltic, the Mediterranean Sea, the Marine Copernicus provides a specific reanalysis, just one product. On the other hand, for the global ocean, the Copernicus service provides a particular product that is an ensemble of 4 different reanalyses. And we'll see why the ensemble is important. Please go on to the next slide. Okay, this is what you can find regarding this product, CMM's product. So you have in particular 2 products that come from the same reanalysis, but they are provided on 2 different grids. A coarse resolution grid 1 by 1 degree and monthly means, and a higher resolution grid that is 25 kilometers times 25 kilometers, and that provides also daily means for temperature, salinity, and currents in 3D, and for sea level and mixed layer depth, just as 2D products. You can find the information on this particular product on the quality information document. And please go on. No, just go back. Okay, this is the table that lists these 4 different products. So you see Mercator Ocean, the UK Met Office, CMCC, and ECNWF. All of them are producing and providing one of these global reanalysis, which have in common the same model, in this case, the NEMO model at 25 kilometer resolution, but they differ with respect to the assimilation system. So why the ensemble is important? The ensemble is important because also the reconstruction of the past state of the ocean, is just an estimate of the reality. There is no exact reconstruction of the past state of the ocean. In this case, we have a 4 reconstruction, and we have the ensemble mean of the 4 reconstruction, the ensemble mean here defined as the sum of the different realization divided by the number of the realization, in our case 4. And we also provide the ensemble spread, that is how much, the 4 products differ with respect to each other. This ensemble spread is our best estimate of the uncertainty related to the estimation of the past state. And it's very important because it gives you, an estimate of how much you can dare that the past reconstruction is accurate, where it is more accurate, where the 4 products are more similar, and where they are not so similar. So this is important, as I said, especially for the climate applications. So in particular, if you go to the next slide, in particular from the catalog, CMEMS catalog, you can download this ensemble mean, the mean of the products, and also, please click, yeah, the standard deviation that gives you the error related to the past reconstruction of the ocean. It's clear, you see here, that the errors are bigger in regions of mesoscale, intense mesoscale activity, like the Gulf Stream, the Kuroshio region, and the Antarctic circumpolar region. How we can use, and how actually we use, this ensemble approach, please, the next slide, Paola, for the ocean monitoring indicators that you can find in the catalog of the marine products. This is one example of the oceanid content. Next slide, please. So yeah, there is a zoom on what you can find. This is the global oceanid content average over the 700 meter, a very important climate proxy because it's telling us how much is the ocean warming during time. Here the time series is from 1993 up to 2018, and you see that the line, the blue line is actually the ensemble mean of these products that we produce, and the shaded area is an estimate of the uncertainty with respect to how much the oceanid content is increasing. The next slide, please. This is another example. This is a temperature anomaly for a specific year. In this case, 2017, but you will find it updated on the catalog for each year. The temperature anomaly with respect to latitude and globally average in longitude and as a function of depth, okay? And you see there are regions, these shaded gray etching regions. These are the regions where the signal to noise ratio is less than 2. So are the regions where actually all the products differ more with respect to each other. The next slide, I think it would be the last one. Yes. Okay, this is just about the training session, so please don't forget to have a look at the training material, and you have the dedicated Python notebook that will guide you through these different aspects of this particular peculiar products, that is the GREP product, global reanalysis product of CMEMS. Thank you very much. If you have questions here.
Thank you. Thank you, Simona. So we have arrived to the end of the first 4 presentations, and we are now ready for reading your questions and reply to them. I will invite the 4 speakers to turn the camera on and also to be brief in the replies, because there are many questions, so we will try to answer as many of them as possible. But yes, we need to shorten the answers. We will provide, in any case, more detailed answers after the workshop. So there will be opportunity to investigate more your questions. Okay, so the first question it's about the presentation from PATS. So what parameters of in situ carbon data do you have in the catalog? Do you have PCO2, alkalinity, or DIC?
I have provided the answer in the next slide, I think. I don't know if you can, yes. So basically you can find all the parameters that are managed by the in situ thematic assembly center in this link. Even you can type in situ tag parameter list in Google and it will appear there. And if you visit this list, you will find all the list of the parameters. And in there, I just copy some of the ones related to the carbon, but I'm sure you can find way more now than I'm sure you are more familiar with them.
Okay, thank you, Pat. So we
Welcome.
go to the next question. Are the products European-centric or global? And well,
I began answering in the next slide that it was both. The region are European. Sorry, we are funded by Europe, but we do have global products.
Yes. So actually what you have seen these 2 days are all the global products, but in the catalog, there are many more products related to this different European regions. Okay, so the next question is why there is not global distribution of sea level rise product in the catalog. It seems that you just have sea level rise from specific region and stations. So
no, we do have, next slide, please.
Slide, yeah.
But they are not in the ocean products part of the catalog, but in the ocean monitoring indicators. You have satellite sea level rise from global sea level rise, and you've got the spatial distribution of these trends all over the oceans.
Okay, thank you.
But they are in the ocean monitoring indicators, not in
the products themselves. Like
yeah. So both are catalogs somehow.
Yeah. Thanks. Okay, so next question is geostrophic currents are the same seawater velocity?
I'm not completely sure about the exact definition of seawater velocity, but I would say that in seawater velocity, you probably have the wind effect, so the Ekman current, possibly tidal currents and such, that you don't have in geostrophic current. Geostrophic current are only the currents computed from the ocean topography. It's about 90% of the current, but still not the full current.
Okay, thank you, Vinka. What is the best available product with native satellite measurement that can be used for comparisons with tide surge models? And I guess this was for Vinka as well.
Yeah, certainly. I'd say the level 3 data available through CMMS are the easiest and the best product. You could try level 2 data, but you'd have to go to the different space agency to get them, and they won't be intercalibrated. So you won't have exactly the same measurement from each individual satellite. So the level 3, you can use all satellites together, but you can still uncorrect from tide and atmospheric pressure too.
Okay, thank you, Vinka. We go to the next question, again for you. Is there a product?
For me or pass?
Oh, sorry, because there is in Situ then. Or is there a way? So the product is
steric.
Yeah. So who wants to reply?
In the end, of course, they can use in situ products for this. Although I don't know if maybe the data is sparse for this kind of study. It's a matter of them to for example, use the training material I have provided and try to select the area of interest and try to discover how many data is there and with salinity and temperature parameters, and see if it is enough for this kind of studies.
Maybe I can add, sorry,
Marco.
my camera doesn't work any longer. Today is not a lucky day, but I can say that of course it's possible to calculate the static component from the reanalysis, because you have the 3D gridded temperature and salinity, so you can calculate both the allosteric and thermosteric component from reanalysis data.
Or you can remove gravimetry data, GRACE data from altimetry.
Yeah.
So it's a wide range of products for doing so.
And with the
Great product are not within Siemens.
With the ensemble reanalysis, you can also have an estimate of the spread.
Yeah.
This
from Argo.
Yeah.
So you have a lot of possibilities.
Yes, different ones. They're reaching about the same result as far as I've seen. So,
no, but it is true that is not a product itself. I mean,
no.
You have to calculate it.
Okay, perfect. Thank you. Okay, this is long. I really appreciate the workshop, but there is sometimes a problem to well understand the organization of data. For example, for the waves in situ parameters, waves height, waves direction, wave period, there is some repartition of in situ files such as dB, DOTB.
Yeah. This question is for me. On the other slide, well, I suggest this user to check the product user manual of the product. I just provided the link of the product, and in there, if you select the tab that says documentation, you will find in there the product user manual, ¿vale? I'm sorry. And in the product user manual, you will find the list of these bgrams meanings, okay? Indeed, not all of the ones you put are the real ones. I just checked the product. And the one you have is DB, which comes from drifting buoys. The other one is MO, which basically stands for mooring, so fixed platforms. The other one is TG, which stands for taigoges. And the other one is SD, that stands for sailrons. But everything is available in this product user manual that you will find in the detailed view of the product in the Copernicus Marine Service catalog. Mm-hmm.
Yeah, thank you, Pat. Yes, we use a lot of acronyms and names for the catalog. So you will learn by going to there and dive into all the documentation, because it explains everything. Okay, so the next question is, does Copernicus host data on typhoon, cyclone, hurricane tracks and speeds? And I don't know if there was a question, sorry, the reply after that or not? No. Okay, so does any one of you know about,
I can answer in part, because I'm part of another project entirely, which aims to be within Siemens in the future, with synthetic aperture radar observation of cyclones, but not yet.
Okay, so stay with us.
If you want to,
you Copernicus, and you will see, you will find them. Yeah. Okay, so has anyone used the altimetry products for storm surge monitoring?
Yes, within the eSurge project from ESA.
Okay, so you may investigate that project. Is there any other question? Okay, that's a question of nomenclature.
I can answer that. I don't know.
Yeah.
Well, basically, the first part is just telling you which TAC or MFC, so the model forecast center, is producing the product. And the second part is the number of the product in the catalog. So is that.
So as you have seen in the Simona Masina presentation about the globe, there are the different regions, European, then the global, and those are the first number. And then the numbers refer to the specific products. So that's the thing. Okay, next question is, the global ocean temperature anomaly at 0800 shows some statistical problems. there are trends of values over and below the mean. How you are dealing with this problem?
I'm not sure I understand this question. We were showing the global ocean heat anomaly, the global ocean heat content anomaly. So that's probably why you are seeing negative and positive values, okay? So it was the anomaly with respect to the climatological value, but I'm not sure I'm answering the question. So if interested in digging more on this issue, you can write me, whoever asked this question.
Yes, thank you. Okay, I think we replied to all the questions. So thank you very much to the speakers, to the trainers of this first part for your presentation, for your replies, for your availabilities. And we have now the break, 10 minutes break, and then we will go on with the practical session about the Jupyter notebooks and the RStudio. So see you in a bit.
Okay, so we are back now for this second part and dedicated to the practical material. You will have some demonstration from Francesco and David. I will just, I wanted to show you again the Padlet and how to access the Jupyter Hub. So on the e-learning material column, you have this square here where you can click on and you directly access to this authentication web page, and you enter your username and password from CMMS, from the Copernicus Marine Service, and then you log and you will be directly redirect on the Jupyter Hub platform. And from this platform, you can practice all the Jupyter notebook. Okay, here they are. So now I'll let the floor to Paola to introduce our first panelist of the second part. Thank you.
Thank you, Fabrice. So again, welcome back. I remind also that those questions that were posed after the break or during the Q&A session that we couldn't reply during the session will be, in any case, managed by the trainers. They will give the answers, and the answers will be available in the same Padlet that you just saw from Fabrice. So let's go to see more live experiences with the data. And actually, no, the first presentation from Francesco is a recap of all the Jupyter notebooks exercises you will find in the Padlet as well. So I leave the floor to Francesco Palermo from CMCC to present the notebooks.
Thanks, Paola. Thank you, Paola. I share the screen. Hi, everybody. Good morning, or good afternoon, or good evening. I don't know. Well, I present now. I give you an overview of all the notebooks prepared for this training session. And let's start with the list of the notebook. There are two kinds of notebook. Those related to models, so in the left part, and those to the observation. So we have 4 notebooks related to physical variables, biochemistry, waves, and reanalysis, and other 4 notebooks for the observation, in particular the in situ observation product, ocean color product, SST observation product, and sea level observation product. First one, 01, about the physical model. We use presented by me, we use the global reanalysis feed 001030. This is the product name in the Copernicus Marine Service world. There are 2 exercises. We presented we present the plotting of maps of MLD and the other physical variables and the currents for winter and summer, and how to plot the transit for all these physical variables. Second one is about the biochemistry model, and here we present the plot of maps of chlorophylls, nitrates for winter and summer. And also we present an exercise for plotting the transect, the vertical sections of nutrients and oxygens. And this notebook is presented by Fabio Viola. The third notebook is related to the wave model products, Elise, presented by Elise, and you already know about these two products. In the exercise, we propose how to produce maps of significant wave height and how to plot the wave rows for 10 years periods. Notebook 4 it's about a reanalysis model, and it is presented by Andrea Cipollone. And here you will find how to plot maps of temperature and the corresponding error, how to plot the transect of temperature and salinity and the corresponding error in winter and summer time, and how to plot the density of temperature and salinity in the transect. It's very similar to the first one notebook. 05, presented by Paz, is about the in situ observation product. Here, the product name. You will find many sub-notebooks for 5 exercises. First one about the data discovery. The second one about subsetting and download. Then you will see how to plot the time series, how to plot the trajectories, and how to plot the profiles. Another notebook about the Shannon color product. Here the product use. You will see how to plot map of chlorophyll data using reprocessed chlorophyll daily time series, and how to plot time series of chlorophyll. 07 about SST observation products, presented by Simon Good. 2 products used and 2 exercises proposed. One for plotting the SST maps, and the other one for plotting time series. You will see also tables of data. Last one, notebooks. There are 2 notebooks about sea level observation product. One about the L4 product, the other one about the L3 sea level product. You will see 4 exercises, one for plotting the data of sea level anomaly, then how to explore the data, select the tract, and geographically set the data. You will see also how to map the dynamic topography and geostrophic currents, and how to map the formal error. Thank you. This was just a presentation of all the notebooks presented available in this training session.
Okay, thank you, Francesco. Actually, I leave the floor to you as well, because now we will going to see an example of this notebook.
Okay.
And after that, if there is any question, we will address the question just after the demonstration.
As showed already by Fabrice, when you reach the Jupyter hub of Copernicus Marine Service, you will have this kind of interface. On the left, you see the list of notebooks, these 8 notebooks. Now I'll show you how to run the notebook 01 about the physical model. You click on the folder and then select these files. I've already opened it here. Here, hide this one. So this is the notebook. The notebooks are very similar between them. This notebook is related to the physical model product, and here you will see how to visualize the maps of physical variables, such as temperature, salinity, MLD, vector currents, and also how to compute the density and plot vertical sections along the transect. Before starting, if you never used a notebook, please consider these two notes. The first one, very important, is that for executing each cell, you have to go through the play button from the top menu. You can find here the play button, or you can find also very useful the keyboard shortcut Shift plus Enter. So I can click here for selecting a cell. You see the blue bar on the left, so the cell has been selected. I click here for play, and the cell has been executed. This is a text cell, so you don't see anything about the code, but it's a particular kind of cell. Table of contents, you'll see all the links for going to the different parts of the notebook. You will see an introduction, then the exercise 1 and the exercise 2. You can click on these links. Introduction, just a few words about these notebooks. I've already said about them. First important part for the description of the exercise about the data. Here you can find this paragraph, you will find all the information about the data. So its name, its descriptions, a table for describing its characteristics, such as the variables available, spatial resolution, etc. But if you want more information, you can go to the related page on Copernicus Marine web portal, clicking on this link. Or you can find also other information, the PDF related to this product. Download the data. You will find here some information about downloading the data. You don't have to download the data running this notebook on the cloud, as we are doing now, because the data have been already downloaded. But if you want to run the notebook on your PC, you have to download the data. So here you will find all the information needed for downloading them. Here is the list of parameters used for downloading the data. Let's consider that you need to have CMM's user credential, that you can get them here, because the data are all free available, but you have the user credential for downloading them. You need to install Motu client. You will find here all the cell below. And please remember to insert the username and the password for at the end of the line, and you can execute this line for downloading the data. We don't have to do it now, so check if the file have been created. Yes, of course, because we already the file on the notebook. Oh, it's not playing. Well, the exercise. At the first, you will see the list of libraries, Python libraries that I've been using during this notebook. There are some very popular scientific libraries. And here, short description of one particular library used. And here you will find all the instruction for installing these libraries. You don't have to run them on the cloud, but if you want to run the notebook on your PC, you have to install all these libraries. You can use this command line and execute them in the empty cell for executing them. Well, let's start the notebook. but it's not working. Sorry. In case the notebook is not working, you can restart the kernel. Okay, let's go back to the libraries importation. Okay, you'll see a number here in the squared bracket if the cell has been run correctly. So let's execute the cell, all the cell. Let's go on. Maybe later you can read all the information about all this cell. One important cell to consider is that one, because here we are loading all the files we have been downloaded before. And after loading the file, we can access the dataset with XArray. If you don't know XArray, which is a very important scientific library of Python, you can see here some very important methods for accessing the data. For example, this method info will show you how to access the most important information about the coordinates, variables, etc. Let's go on. There are many descriptions about how to access the data. Let's go to the configuration. We set the cell for configuring the plot. Let's go on. No, it doesn't care now. Here, very important cell, because here we can set the variable we want to plot. So we selected the MLD variable. You can command this one and select another one if you want, change the variable, but we don't want. So execute this cell. Let's go on. You can set also the bounding box. We selected the full area for now, but you later can change it. The minimum and maximum value of the color bar, the depth. Let's go on. The plot configuration, for example, is width and height. And then we are setting the cell for the map generation. This long cell, very long. We can execute this cell for plotting the requested map. Here, you can see the two maps for the 2011 and 01 because it's winter, and 2011 for 08 for the summer. Please, let's try to change the plot. As I said, you can change the variable to plot. You can change the area, the minimum, maximum values, the depth level. So enjoy. You can click on this link for coming back to configuring the variables for the plot as presented before. And let's go on. Now we can generate the map of currents. So execute this cell needed for setting again the plot, area, minimum, maximum values for color bar, etc. They are very similar. The code are very similar. And now, after executing this cell, we have the currents velocity. Okay. Even here, you can try to change the plot, going back to configuring the variables from this link. Last exercise about the plot of transect. We use the same data we used before. So if you want to go back to the data, data descriptions, click on these links, previous exercise. The data have been downloaded in the same way. So let's go to the exercise. Here we set the configuration as we did before. In this case, we set the minimum and maximum depth, the latitude point, which is fixed one, just 1 point, and the longitude, the minimum and maximum values. So execute this cell. Set the data set we will use for plotting the transect. Don't care about this cell because all of them have been used for configuring the variables that will be plotted. Well, here configure the variables for the plot. We set these 4 variables. that we will use for plotting the transect. So run this cell. Set the parameters for the plot as before. You can change the, for example, the size for the plot, also the labels. So this cell is for changing the plot configuration. And then finally, you have to load this function, this method that will be used for plotting the transect. We are ready for plotting, for example, the temperature in winter and summer. So as you see, the data will be related to temp, but you can change them to other variables. Run this cell, we set the title and to plot the transect. You can see here the two plots for temperature, for winter and for summer. We can do the same for salinity. As you see, data is now sal, which stands for salinity, the two plots. And finally, we can see the comparison between the density and the MLD. This is a particular kind of a plot that we are generating. So run this cell for plotting the density, which set all the information of the configuration for plotting this kind of for defining this kind of plot. Run this cell, and now we are ready to plot this this map about the. We are ready to plot the density. Here you see the density, also the MLD, which has been calculated by the libraries we imported at the first part of the notebook. You can see this black line. And then, as before, you can calculate again the density and plot the data. Now we set j equal to 1 because this is an index for changing the data we want to show. Before we selected j equals 0 for the winter 2011-01, and now we selected j equals 1 for the summer. You can see here 0.8. As before, the transect and the plot of the MLD curves. Thank you for the attention. We are sure that you enjoy all this data, and thank you again.
Thank you, Francesco. Thank you for this example. I don't know if there are questions. I think there weren't specific questions on the notebook, but maybe general ones. But shall we reply later? Okay, we will reply later. So thank you again, Francesco. And we pass to the next practical session, demonstration about RStudio made by David D.March and Morlà. And so thank you, David, and the floor is yours.
Thank you very much, Paola. Hello, everyone. I'm gonna now try to share my screen. Perfect. Great. I assume you can see the screen.
Yes.
So hello, everyone. My name is David Marc, and in this training session, I'm gonna show you how to use RStudio to work with Copernicus marine data. So I gonna assume you have a basic, you have some understanding of RStudio and working with R, but I'm gonna then show you a demo so we can see all of them together. And the idea of this tutorial is to show you how to import and inspect NetCDF files plot maps, especially we're gonna work with a gridded product from a numerical model. And then I'm gonna show you how to extract values from this data. I've been working extensively in R, especially in topics like marine ecology and conservation. And this could be one of the most popular tasks that we all need to carry on to once having our sampling stations, line transects, or even polygons representing, as in our case, the testing in this demo, a marine protected area, how to extract information from here. And for running this tutorial, we have different resources. You have access to the R script we're gonna check, and in addition, there is manuals in PDF, HTML, and also a video tutorial that can also explain you more in detail some of this tutorial that at this time I'm gonna try to move more faster. This is the website where you can get access to the training materials that I mentioned. And similarly to the Jupyter notebooks, we can see this tutorial in a very similar way, where we can find here information about the where to get access to RStudio, how to download, and especially more information about the sampled data that we are gonna use on this tutorial. Unlike the Jupyter notebooks, this format does not provide us a dynamic way to run the code. So what I'm gonna do is to switch to RStudio, so everyone can see how to run this script, and we can see what the different actions are moving. So first thing, as you can see, I have this is the first screen from RStudio. I have just opened this tutorial.r that contains the script that you can get from the Copernicus website. You are gonna see that the first step now is to install the different packages that we are gonna need for this tutorial. They should, so probably most of them are already. Do you want to install sources? You can see that they get downloaded. It takes a while, but this is quite straightforward. In case all these packages have been tested and should be working fine. What we are gonna do now is to import them. So we are gonna load all these packages. You're gonna see here in this panel the status of the console here. We haven't had any error. All these messages are just reporting the potential dependencies and masking some of the functions, but there is no problem for that. For getting the data, you already have the data in the folder, but I also have provided you some codes in order to retrieve this information from the website, so you can download the two products that we are gonna use. The first one is a data set from Copernicus. This is a numerical model. It's more detailed. For example, here in the notebook, you can find here, this is from a global physics analysis and forecast. You have here the detail of the product. You have here as well the parameters that I've used to select this sample data, so you can easily reproduce the access of this file. And the other file that I prepare is the boundaries of the Galapagos Islands Marine Protected Area. So we are gonna use this layer. This is a GIS layer that we are gonna use then to extract the information. So as you can see now, I have this subfolder here, data, with these two files that we are gonna then use now in the tutorial. So the first part is now to inspect an HCDF. In R, what we can use is this function, ncopen, and then we can print this object. When we print this object, I'm gonna expand further this part of the console. We get all this information. You have seen in previous presentations how the NetCDF, the information they contain, and here what we can see is that this product contains one variable, in this case, this is the seawater potential temperature. We have 4 dimensions here. We have the time, the depth, the latitude, and the longitude. And in addition, we have the global attributes that provide further information about this product. So to further work in R as a gridded product, we are going to use the raster package. The raster package is going to import this netcdf. If we just print here the name of this object, we are now going to have some information about the raster object. We're going to have that we have only one band. These are the dimensions in terms of number of rows and columns. We have the resolution of this product in degrees. This is the spatial extent, the coordinate reference system, and the number of the file, the name of the variable. And also what we can see here is that this product corresponds to January 2020. This is a monthly product of sea surface temperature, and we get also this temporal information. And we can use the basic plot function in R. What we are going to see now is that we have now a plot here in this panel where we can see the map of the sea surface temperature. This is some kind of a basic plot functionality that is very useful for doing a first exploration of the data, but then we are going to see some other functions to create some nicer plots. But as I mentioned, this is a product that is a monthly data throughout 1 year. And the point in R, and this is quite common, if we use this raster function, we are going to get only one band. In this package, what we need is to use this function. The function is called brick. If we want to import all layers, as we can see now, if we go to the description of this object, we now have 12 layers, 1 for each month. And if we want to explore, I'm going to introduce this other function. It's called level plot. It's going to take a while now to load because this is more data now to have, but is some kind of a fast way to explore multi-band products that they share exactly the same spatial extension and even share a common legend. So we can have a plot of the 12 months and explore this information. It should take a while now, so we can have this. You can customize the colors and several aspects here in this one. What I'm gonna show now also is how to use some of the statistical tools from R and the raster package. So what we are gonna do now is to calculate the average and the standard deviation of these 12 maps. So we can, using this function, the calc and specify in here the function we want to use. We now can visualize the product here. This is the average. We then have also the standard deviation. And I'm gonna now also introduce you another way to make plots in R, that is using the ggplot package. ggplot package is more advanced library that can help us to combine different sources of information. For example, here I'm gonna also to get a country layer from the natural earth package that we are gonna use as a landmask in our plot. In this case now, as you can see, the syntaxis is more complex as we have more elements. But in this case, the ggplot function works on some kind of a concatenation of different elements. And we can see now the result of these lines of code, but we have that we are adding here the raster. This is the sea surface temperature map. We can also specify the layer colors. We can add this country map on top of the map and define the spatial extension. So this is a package that is gonna give you some nice capabilities for the plots. In this case now, I'm gonna now to go for the next exercise. That is now getting the boundaries of the Galapagos Islands Marine Protected Area. In this case, this boundary is stored as a geo package. For those of you that are more familiar with GIS formats and the shapefile, this is an alternative, a more modern alternative to the shapefile. It's an open format and it only requires a single file. So we can use this function from the SF package in R to import the boundary of the marine protected area. We're gonna again use a basic plot function to see the map. And as you can see with this map, we can see the boundary, but we miss something. We miss some information, contextual information, to really know whether this map is really pointing to the Galapagos or to somewhere else around the world. So we are gonna use another package. This is the leaflet package. It's a dynamic way to represent the spatial information in R. So first of all, what I'm gonna do here is to create a color palette for the sea surface temperature map. There are more details in the notebook, so you can all these functions are more provided with more details. And again, we are gonna run this concatenation of functions that basically what we are providing here is the use of the Esri ocean base map in our map, adding the sea surface temperature, adding the legend that we have here, and adding finally the boundary of the marine protected area here in green. And the nice point of this type of visualization is a dynamic one. So we can combine here on this type of plot the sea surface temperature together with the marine protected areas, and we can explore further this type of map. So we can see here the Galapagos and the boundary of the marine protected area. So now the idea from this exercise is to get this boundary, extract the sea surface temperature values that we have for every month, and get the average and the standard deviation. So for this, we are gonna use this function extract, and we are gonna ask to use the function mean first and then the standard deviation. As you can see, these functions are quite fast. And finally, what we are gonna do here is to plot the time series of this information. For this, working in R with timestamps can be a little bit challenging at the very beginning. In this case, I highly recommend the Lubridate package and this type of functions that you define the way that, so if we go back, sorry, to this multi, this is the monthly map. As you can see here, the dates are codes on this way in a year, month, day, hour, minute, and seconds. So we can use this information to get now the dates. This is basically these lines of codes is to get this on a nicer format. Then we are create a data frame. In R, the data frame is a type of object that is also very common. And as you can see here is some kind of a spreadsheet, a table, where we have here for each of the months, we have here the average and the standard deviation of the sea surface temperature. So and the last part of this now is gonna to use again this ggplot package, where we are gonna represent the time series. So as you can see here, with this we can represent the average here. The shaded area represent the standard deviation, and is a potential way of combining the capabilities of R and the graphic displays that we can get from R and plotting this information. So that's all from my side. We've gone through the tutorial. Thank you very much for your time, and I hope you have enjoyed this demonstration. Thank you.
Thank you, David. Thank you. So we now have a few minutes for addressing any questions to both Francesco and David, if there is any. They are coming. Okay, actually, this is more for for Fabrice. The question is about logging to the Jupyter Hub Siemens Mercator Ocean France, but I cannot see the notebooks.
Okay, perhaps you need to log another time, or you have to dive into the folder to see the different notebooks, because when you start, you will have the shared notebooks directory with, you have to click on Training America, and then you have the different folders with the different Jupyter notebooks and the dependencies for other notebooks.
Okay. So the next question was, what is the link to get into the Jupyter with the shared codes? And I saw there is already the answer here. So it's
yes,
the Jupyter Hub Siemens Mercator Ocean France. Can you please let us know whether we can run this in the cloud? Is all the Copernicus data on the cloud?
So we put at the disposal of the participant the Jupyter Hub environment, so you can use these practical exercises directly on the Jupyter Hub. If you need a cloud environment or computational resources to launch your own code and play with the Copernicus data, I encourage you to connect to the Wikio platform. Wikio is the data information access service developed by the Copernicus services and EUMETSAT. So if you go on this platform, and it's free like the Copernicus Marine Service, you can register and you will have access to a dedicated Jupyter Hub on from your dashboard, and you can upload all the Jupyter notebooks you want and play with all the data from Copernicus.
Okay, thank you. Now, how can I calculate the mixed layer depth from temperature, salinity, vertical profile by using Python codes and RStudio? That's, I guess, some complicated question. I don't know if...
I can answer to this question. I don't know. But you have already the mixed layer depth available on the datasets.
Yeah.
Yeah, and for RStudio, there is a package. It's called OCE, that they contain some functionalities for oceanographic products. And to my understanding, I think there is a specific function to get also the mixed layer depth.
Okay, thank you, both. This is another general question. Unfortunately, I cannot launch any of the notebooks. Is there a technical support email where I could ask for assistance after the seminar?
Yes.
And
yes, you have this address. You have this address. You can write an email to this address, and don't hesitate to share with us where you have these blocking points on the Jupyter notebook, because I test again live and it's working for me. So I hope it will work for you.
Okay. This, I think, was like a reply to the previous question about the mixed layer depth. No, okay. Can we modify the code for the boundary I don't know to which it refers.
I don't know if maybe they refer to the boundary from the marine protected area. If this is the case, absolutely. You can change and use any type of polygon shape that you want to use, and then you can reuse the code to extract information. You can use for, of course, for any other type of any other marine protected areas. Is also quite common to use in conservation. For example, use jurisdictional waters. You can use economic exclusive zones, and then summarize information that is within the polygon, but also not only polygons, lines or points as well.
Okay. Okay, is there any other question? No, it looks
yes,
like
and
not.
just to add, you can also change and modify the Jupyter notebooks. And if you saw some boundaries on the Jupyter notebooks, you know that you can change these boundaries and launch again the cell to apply the new conditions.
Okay, thank you, Fabrice. So I think there is no more questions. So just to remind everybody that after this training session ends, you will receive a thank you email, and in this email you will have the possibility to get the link to the direct access to all the materials that we have seen or partly seen during these 2 days. Also, so the access to the Jupyter Hub, and there is also the important aspects of the survey for your feedback on the on this training, which help us in improving the training for the future. So I think I said all, and before passing to Fabrice for the last say, I would like to thank you all from my side. From me as the moderator, to all the panelists and the speakers and the trainers that have worked not only these 2 days but also previously to prepare all the material. Thank you very much for your excellent and very helpful work, and thank you to the participants. I hope you enjoyed and I know it's a lot of information altogether, but hopefully this is just to raise your curiosity about the Copernicus Marine Service data available that may be of use for you, and so that you will have the time to get more into the catalog and the data. So thank you from my side.
Take the time to discover all the material we collected for you on the Padlet, because there is a lot of information. There is a user manual with all the explanation to copy your codes and the Jupyter notebooks, etc. And just last information about the Jupyter notebook dedicated on ocean color. It will be available tomorrow or on Friday. So be patient for this one. And thank you very much, Paola, for this moderation, and thank you, Vincent. Thank you to all the panelists and Christian also to manage successfully this session. And good luck with the training and the material, and don't hesitate to contact us or at training CMMs or the service desk. Okay. Have a nice evening, night, afternoon, journey. Thank you very much.
Yeah. Thank you. Bye.